parenthesis, I'm not. Ilya, can you mute Elisa as well? Thank you. All right. All right. So how did those the word embeddings or the class embeddings learn the similarity structures among themselves? Is via the other. So how did, let's say, two words that occur together with a particular class they learn the representations that are close to each other is because both of those representations had to align very well with the class embedding that both of them are associated with. Right? We'll just ignore this one to a nice background. In fact, in modern office, they actually have all those, let's say, not the microphones, but the speakers on the ceiling, if you have noticed, that actually creates white noise. They are in the background. That actually helps people, let's say, not being distracted from the other people talking, which is precisely the opposite of what we want in this particular case, because we want you to focus and then listen to me. Oh, well, it's okay. What can we do? So, and then the interesting thing is that there is a weird, let's say, kind of bipartite graph-like structure, right? So for each class, there are examples where the examples correspond to a text, and then each text snippet consists of the multiple words. So you can imagine that there's a one word that appears n many times with a particular class, and then that word is going to also appear with another class for some different number of times. And then you can see that there is a bipartite structure. And then by looking at which other, let's say, classes or which other words that these particular words of the class are respectively associated with the learning process, we'll learn this representation that reflect the similarity. Now, what does it actually tell us about the similarities? The similarities, when we think about the similarities among the words or similarities among the classes, the notion of similarity is defined with respect to the problem you're solving. It's not an absolute notion of similarity here. And then this is a really interesting thing because when we think about the similarity between any two concepts or the words that you have in your mind, let's say cat versus dog, against, let's say cat versus, let's say rail, you do feel like you have some particular, let's say, of the similarity among these different words. But then what we have learned last week is that in fact, that is not really the case. How this machine learning system or the deep learning systems are learning these representations is to look at how they are related to each other in the context of the problem that is being solved. So let's imagine a sentiment analysis example that we thought about. So we're doing a prediction of whether a given review on Amazon, let's say, is positive or not. For that one, it's pretty clear that so the love and like, they are probably associated well with each other. So their similarity among these two words has to be quite high. Love and hate, yes, they're going to have a very high level of the dissimilarity because love probably is well associated with positive label, while hate is probably much more so with the negative label. But what if we actually use the exactly same set of the input reviews that the problem itself? What if? Well, let's try to mute yourselves. It's been a year and a half of the pandemic using Zoom. So so always mute yourself when you join. All right, good. But anyway, so let's say we want to change the problem itself. What would be an interesting example? So perhaps now what I want to do is to try to predict the category of a product to which a given review in fact belongs to. So you want to think about, so a review has been uploaded, you want to figure out which product this review is about. Now, why do we want to do that? Because often the reviews are not really about a single product. It does talk a lot about the multiple products, although those reviews are written in a particular product page. So I want to build a classifier that's going to tell me which product this review is about. maybe it's not necessarily obvious from just looking at which page it appeared. In that case, love, hate, the similarity, are they actually similar to each other? Are they dissimilar to each other? Doesn't really matter. We don't really get it because most of the products are going to get a lot of loves, a lot of hates, and depending on what kind of product, but on average, you're going to see that some people love it, some other people hate it. So then I think those two actually are neither similar to each other nor dissimilar from each other in this context of trying to predict the probability. So what that means is this similarity really is all about the problem that we are solving. That's a bit dissatisfying, right? Or is it satisfying? It's a bit dissatisfying in the sense that what that means is that the similarity that these deep neural nets are extracting are all dependent upon the choice of the problem. So then what is the problem we want to use? So what we ultimately want, one of the reasons why we always are interested in kind of getting some kind of representation of input or classes or whatnot is because we hope that the underlying structures that have been uncovered from by this kind of learning process is going to be transferable or useful for other problems as well. So if I knew that the love and hate are very dissimilar from each other, while love and like are similar to each other, if I could get that kind of information or the structure behind this data by solving the problem of sentiment analysis, imagine that I can probably use the very same representation for solving other types of the problems where I may not have as many associated labels as possible. So that's what we want. What we want is not only to solve a problem, but by solving a good set of problems, we want to be able to use the underlying regularities that have been extracted from these deep neural networks or the classifier for other problems in the future. So because of that, we want to choose a good problem. Now, let's think about what would be a good problem. If we have to somehow pick one problem that we want to solve, that is that based off of which we can actually get a good set of representations that are going to be useful when we try to solve other problems in the future. What would be such a problem and then why? Sentiment analysis is definitely not the case, right? Okay. Translation sounds good. Why would translation be a good problem?
You're trying to represent the same thing, thereby ignoring the underlying.
I don't know. Too fluffy for my kind of taste. Okay. All right. Back there, yes.
Predict the next word, predict the next sentence.
Predicting the next word, predicting the next sentence. So why would that be a good, let's say, task or the problem to solve?
Seems pretty general.
Seems general. Still too fluffy for my taste. Okay. Anybody else? All right.
Perhaps language model.
Language modeling. So okay, but what is language modeling? What do you mean by language modeling?
You might have a chance to learn the distribution of the language that you're working on.
Okay, but why is learning a distribution useful to get a good representation?
Perhaps you can use the previous context that you encountered.
Too fluffy still. Okay. All right. What else? What else? Let's be creative.
Summarization.
Summarization. Okay. Summarization. So why is summarization a good thing?
Because we are using some frameworks to
Okay. I see. Okay, I like this. So the summarization might be a good problem to solve because in almost by construction or the definition of the problem, we are ensuring that the representation of the words or the representation of the two different texts that were written two different ways to be similar with each other in the meaning space. Okay. That sounds reasonable. Yes, yes.
Maybe at least task your like the relationship between different words, and what you're trying to say is important. That's true in translation and also summarization. So you're learning these underlying structures in the language rather than just like sentiment analysis, which is like this is a positive net.
I see, I see. So yeah, I mean, that's good. That's a very good follow-up to the summarization in the sense that so what we want perhaps is that we need to be able to come up with a problem that's going to allow us to tell what are the things that appear in a similar context when written in text. Could be summarization, machine translation. In the case of machine translation, what are two words written in two different languages, right? Or the two words from two different languages that appear together, right? In the translation pairs. Perhaps that's a good thing. Okay, I like that. I like that. So before we delve into the gory mathematical details, it turned out this is actually a really difficult problem to imagine, and a lot of people have been thinking about it over more than half a century. In fact, I don't know if you have noticed, but the Quran Institute of Mathematical Sciences at NYU here is houses in multiple buildings, but the main building is Warren Weaver Hall. It is named after the mathematician Warren Weaver. Warren Weaver wrote a memorandum titled Translation in 1949, if I remember correctly. And then in that memorandum, Warren Weaver actually did mention that what is the right way for us to represent a word when each and every word, you can imagine, often has multiple meanings or multiple senses. So the typical and very boring example is a word bank. Bank might mean a river bank, or is a bank as a financial institute. So what is the right way for us to represent this meaning? And then what is the right way for us to disambiguate between these two meanings of the word bank? How do we do that? So if you have only just one word, clearly you can't do that, right? It's impossible. But how do we actually decide which of these two senses of the word bank that we use? Context, right? So by looking at the context in which this word appears, we can now determine out of many possible meanings of this word, the bank, we should use, or that we should understand this word. And that's actually an interesting thing. So if I just go one step further, perhaps we can even say that the meaning of any word, in fact, arises from the context in which it appears. It's not really the choice of, or the choosing one of the set of given, let's say, senses or the meanings of a word that we, context helps us, but perhaps the context itself is the meaning of a word. So what does that mean? What does that mean? So perhaps if you think about all those, let's say, the nice poems talking about how it's beautiful to sit on the riverbank to think in the spring days or so on, those poems actually tell us about the meaning of the bank in the sense of the riverbank. And then you go read all those articles from the Wall Street Journal, and then almost every single article in Wall Street Journal does mention bank. And then, but by looking at all those articles where that bank appears, you see that I don't know. I mean, why is that? Because the Wall Street Journal journalists actually are the best investigative journalists in the world at the moment. So then you do that, you collect it, maybe that is the meaning of the bank as a financial institute. So perhaps it's not that there is an intrinsic meaning from which we actually get the intrinsic meaning of any given word, but perhaps the fact that that word appears in a particular context often tells us what the meaning of the word is. And then that is what we called, or what the first in early 1950s called as a distributional hypothesis. The idea is that you can imagine that let's say you are going to you got to know a new person, you got to know a new peer in your class. What is the best way for you to know who that person is without actually talking to that person? Because the person might be the someone you never want to actually talk with anyway, right? So what would be the one thing that you do? You're going to actually look at who are that person's friends. Right? You look at who the person is hanging out with, and then you can get this sense of who the person is. And then distributional hypothesis is precisely that. We can get the meaning of a word by looking at what other words it actually appears together with. Now that actually tells us a lot about what is a reasonable way to get the model that's going to get us a good representation that reflects the similarities as well as the dissimilarities among different words. And then what we're going to do is that is how we actually get to the idea of language modeling. Now, obviously, we haven't actually talked about what language modeling is, and then there is going to be the key concept that we're going to look into today. So when we think about, when you say language modeling, it actually does mean a lot of different things. In other words, because as the name suggests, all we want to do is just model a language, right? So you choose a language, how would you model it? So if you have to imagine what this modeling a language would look like, what would that entail? Any suggestions? Training on neural net is too, the obvious. We're going to learn that anyway. So other than that, yes.
Represent all the words as like particles that mean very specific things.
So the question is how? Yes. Okay. So how would you do this? So the modeling of language, yes, that's a good point. In a sense that if I have all possible text, right, as short as just one word, all the way as the multiple articles, right? We're going to consider each one of them as some kind of particle in this word, and then trying to see what are the meanings of them. But how would you go about it?
You learn the structure and the grammar and how they relate to each other.
I see. Okay. So you learn the grammar. Okay. So that's actually often what we.
Siri.
Did I say Siri? Well, yeah. So you see why the natural language processing is difficult. Right? So your grammar, right? So that's often what we learn. So you can imagine that. So almost none of us actually remembers how we learned our own, let's say, mother tongue. No one actually remembers that. It's impossible to know. No one can actually tell you, or no one can tell me that how they learned this. But if you imagine learning a second language, right? A language that you weren't raised in, then suddenly you realize that what are the how we actually learn the language. And then one of the first things that you learn, if you learn it from schools or some kind of some kind of courses, is the rules of language, rules behind language. What are the words that can follow another word? Or if I wanted to say something in another language, what are the set of the rules that I need to follow in order to create the sentence or the text? And then those rules or the collection of those rules is called grammar. Now, it turned out, unfortunately, we actually don't have a good grammar for any language you can imagine. We all think that we may have a perfect grammar, maybe for English, maybe for Korean or not. Turned out that we don't really have for any language you can imagine. There is no natural language. For programming language, you actually have a perfect grammar that generates it. But for the natural language, we actually don't have any language for which we know the perfect grammar that explains any sentence that we write. And this is interesting, but if you think about it, that's true because you go to the, let's say, recording of this lecture, trying to listen to what I say, you'll notice that not a single sentence is grammatically correct. You'll be surprised. You'll be surprised. I had been surprised quite a lot of times in the first, let's say, 3 years of teaching, but not anymore. I'm like, okay, so I give up. This is just how it is. And then, indeed, that's true. And then, what does it tell us? It tells us that conveying a meaning via natural language has actually very little to do with how grammatical your text or speech is. To a certain degree, being grammatical helps, but not being grammatical doesn't hurt that much. It's an interesting thing. So that's a great idea. It turned out that that's not that easy. Any other suggestions on how to go about it. Okay.
Figure out the probability of the next word given the previous.
They're getting too far. But the thing is that why would actually try to predict the next word, given the previous words, help us model the language. We do not want to actually, counterpoint. We do not want to actually predict what the, let's say, 5 words in the future should be, given all the previous words, instead of the right next word. Or should it be the other way around? What if you look at the future words and then trying to predict the past words? Why necessarily the next word prediction? We'll get to that actually. That's like 80% of this process. Yeah.
Oh, no, sorry.
You can see like how similar sentences that have like slight changes, like those words would kind of be close to each other in some like vector space. So like if you have the Wall Street Journal, it's like this banking institution got indicted, and then later on you have like this financial institution got indicted. You can impute that bank or finance or similar, even though you don't have it.
I see. Okay, actually that's a great point. So the suggestion here is that what if we model language by looking at all the neighboring, let's say, sentences or the text. So I have, let's say, one text snippet that I want to model, or model is meaning of. Then can I just look at all the other texts that are very nearby in terms of, for instance, edit distance. Right? So you may have remember from the algorithms course or not, edit distance simply looks at all those words, and then look at 2 sequences of the words, and then trying to see what is the shortest way or the shortest, smallest number of the changes I can apply to one of the sequence in order to get to the other one. And then the operations that are allowed are insert, replace, and delete. So yeah, that sounds like a good idea. But now it turns out one of the things that makes natural language quite interesting, or any kind of language quite interesting, is the fact that the meaning of these larger units does not necessarily correspond to how the surface form looks like. So for instance, let's go back to the sentiment analysis case. Let's say somebody wrote a very long sentence praising this particular, let's say, move. But then the person was naughty and they just put not again, right? Just a one, let's say, in terms of the distance 1 away, but the meaning kind of flipped completely. So yeah, all these I think ideas are good, but it turned out that the bit easier way to go about is indeed to go into the root of the probability. And then that's what we've been doing already for 2 weeks, is that every time we have some problem, we're going to try to think about how to solve it. But then how we try to solve it is that what if we can build some kind of machine learning system that is able to score some of the input or input and output pair, and then you have to turn the score into a probability. And then for the modeling of the language, we're going to do exactly the same. What we do is to treat any given text, let's call it X, as a sequence of many tokens. Now these XTs are all a part of a vocabulary, just like in the text classification problem that we looked into last week. And then you can imagine this as some kind of text. But again, we're not going to care too much about what this vocabulary is, beyond the fact that it's going to be a finite set. Now, given that one, what we are going to refer to as language modeling is to figure out what is the probability of any given text. So given somebody gave you a text, we are saying a reasonable language model should return what the probability or how probable or likely that text X is. So that's language model. Pretty straightforward. And then the interesting thing is that at this level of abstraction, we could very well, let's say, predict the next word, predict the 100th word, or not even predicting individual words, but all of them together. Then we're going to go through all those different ways to parameterize it. But the goal of language model is to answer this question, that is, how probable or likely any given text X is. So that's the goal of language model. And then when you run into this kind of, let's say, estimating probability or the distribution over multiple variables, because we have multiple variables here. In fact, we have an infinite number of variables, but let's say we're just considering a single text snippet of length t, and then say that this t is just fixed for now. There are many different ways to rewrite this probability. One way that is simplest but most useless is fully factorial, let's say, parameterization. And then in this fully factorial parameterization, we say that all these words that appeared in this sentence or the text snippet is independent of each other. Now you can see why this is probably useless. Let's imagine an example. Let's say, pick any sentence that comes into your mind, and then think about how likely or how probable each and every word is in the sentence. And then what you're going to do is you're going to just multiply all of them to get the probability of the sentence that you're thinking. Probably has nothing to do with it. And then one of the biggest issue is that it doesn't know about the order. So it's going to tell you that the probability of the sentence that you're thinking is same as the probability of the same sentence, but with the shuffled words. And then that's precisely now what we think is plausible. Yes, no? Sometimes, right? Sometimes, because there are some languages where you can actually make a choice of the representation so that the order actually doesn't matter. But still, you can imagine that it's a bit too radical to think that the probability of any given text is simply the product of the probability of individual token or the word without taking into account which other words would actually appear together with. And this goes against the idea of the distributional hypothesis, which we're going to stick to throughout the entire semester. The second one is to rely on the chain rule of probabilities. And here, what it says is that the P of probability of this sequence is going to be rewritten as the probability of the first selected word. Doesn't have to be the leftmost one or the rightmost one. It doesn't really matter. We're going to pick any position and then say that, okay, what is the probability of the word? And then we're going to multiply that with what is the second word that you're going to choose, given the choice of the word in the first position. And we can see the pattern. We're going to do the same thing once more. That's arbitrary. You'll get it. So, and then we do it all the way to the end. So what is this order? O is just an arbitrary ordering of a random variable. As long as you just choose this O function, that's going to take as input one of the t, and then it's going to give you another t. So it's a permutation, so that it is one-to-one and unique mapping between the source and the target domains. Then arbitrary ordering works, and then that's what the probability theory actually tells us, right? So if I am looking at the joint probability of however many variables I have, I can always rewrite it as the probability of one variable times the probability of another variable given that variable times probability of yet another variable given the previous two variables, and on until we exhaust the entire, let's say, random variable. Now, often the choice that a lot of people take is that the OI equals to 0. Because in the case of the text, we do notice a very special structure that it is a sequence. So we often choose either the left or right, and then just go one variable at a time. The third way is a Latin variable model. And in fact, we did look at the Latin variable model briefly in the first lecture. We look at the mixture density network, which is just a conditional version of the Gaussian mixture model or the mixture of Gaussians. And in this case, what we do is we're going to introduce another variable that is called z. And we don't observe it, we just introduce it ourselves. We don't observe it at all. And then we rewrite this similar to this fully factorial version, but we condition each and every token's probability on this z. We're going to marginalize out this z. So what we are saying here is that we have all these words, there are random variables. We're going to introduce a new variable z. And then our so-called generative story is that given the value of c, we can choose the word at each of the locations. And we're going to try all possible c, and then marginalize them out or sum them out, and then we get the actual probability over the word. This approach used to be used more often for language modeling until about 2010. Nowadays, second approach is used more often. But then these two are essentially just two different parameterization for solving the same problem. Yes.
Do you have an example of like what z would be?
Z could very well be just a d-dimensional vector real value. This John distribution encode the positional encoding. No, I mean well, we have the position information. We know how many random variables there are. So that yes, of course we know that this is a random variable that corresponds to the first one, random variable that corresponds to the second one is x2, and t is going to be a random variable that corresponds to the last one. So yes.
Last one is like the first one with the factorial.
Nope, last one is not like the first one. First one doesn't have z. This one has z.
But still there is the product.
There is a product, but there is conditioned on z. If we knew the value of c, yes, then it's fully factorial. But we don't know the values. So we need to consider every z. We have a question showing up there. Oh, I don't know. But how do I see that? Oh, there you go. Can z be interpreted as meaning or intent? If you want, yes. But it's okay. We don't have to put any semantics into z. This is a, the name suggests it's Latin. Something that is hidden, we don't really care about the semantics behind it.
For the number 2,
Yeah.
the chain rule probabilities. My understanding is you try to not include. So when you pick I equals I, you try not to include the words that have an after that word.
Yeah. So if we use O of I equals I, that automatically happens because the same as probability of x2 in next one. It doesn't include it. So O is just an ordering, it's a permutation. So O chooses a single permutation of these random variables. Well, we can do it.
Ordering the thing.
This one can be ordered dependent, can be ordered independent. That depends a lot on C. That's how you encode the information. All right. So, as I said, the most popular one these days is this using the chain rule of probability, which sometimes is called as the autoregressive modeling. And the term comes from the signal processing literatures. So we're going to look into this autoregressive modeling throughout this, let's say, lecture today, and then next week, and then the week after as well. So that's it. Okay, so this is how we can parameterize this probability of a sentence or the text. So then, what is the goal of language modeling? What should be the goal of language modeling? The goal of language modeling should be that the probability of a sentence, I'm going to use theta to indicate that we have a language model, and then this theta is a set of numbers that characterize what this language model is. The probability of let's say, text x is greater than probability of text x prime if X is from the true distribution of language. So let's call this D star as the true distribution of language. But X prime is not from this true distribution of language. So let's imagine that there is some, let's say, oracle that is a D star. This is a distribution. And then every sentence that we write or that we speak in any given language, let's say this, if I compute the probability under this D star, that's perfect. This one actually only puts the probability on sequences that form the valid text in that language. And then our goal is to have a language model that is almost always going to put higher probability on a likely sequence than unlikely sequence. That's what we want to do. So in other words, we want to ensure the probability assigned to a valid sequence sentence is higher than that to an invalid.
Wait, Professor Cho, what is the if X and then the squiggly thing mean? Like, and then there's like another, like, is that and?
%.
Okay.
Theta is just an arbitrary parameter for a language model.
Well, theta, we're going to estimate it. We're going to estimate it ourselves, but you can imagine that you have any given language model. Any given language model, there is associated theta that we can actually characterize or the identity.
So that's what we learned.
We can learn it, yes, or somebody can just give you that as well. Yes.
Do we care about the probabilities between two valid X's or no?
Yeah, that's a very good question. So if you have two valid sentences that were drawn from D star, we want our language model to respect the probability difference under this D star as well. But that's pretty difficult, not because it's difficult to use a kind of example or they impose a kind of constraint, but because we don't know how to check it. We actually don't. We can write, let's say, two perfectly valid sentences, but then you have the, how do we know which one is more likely? Unfortunately, that's a difficult problem. So what this tells us is that if you look, if you actually focus on this part, what that means is that this is unsupervised learning. So language modeling does not have a label or the target. It's all we get is just input. So we have a machine. So often when we imagine machine learning, we have some black box. Then here's something input going in, and then this black box should give us some output. And then we try to make this black box to output something. We train this black box so that every time the output is wrong, we say, okay, that's wrong. Here's the correct answer you should have said, right? That's what we have been doing. That's the supervised learning. Here we actually don't have that. This black box is going to take us input a text snippet, and then it's going to give us just a single number. But we actually don't know what is the right probability that should be given to any given text. We actually don't know. So that's why this is an unsupervised learning. And then that's what makes it so much more interesting than text classification. So now we know what is the goal of language. We know what language modeling is. We now know the goal of language modeling. What do we need to do? We need to think about what is the learning process or the learning strategy we can use. And then second, we need to be able to parameterize these conditional probabilities, just like what we did with the text classification. And in fact, there are a third one, but third one, we're going to talk about it next. So let's talk about the learning first. In the case of learning, it's really interesting. So what was the kind of, let's say, criterion that we decided to use for training any neural net in this course from last week? I did say this, right? I think I did. So what do we want to do? Well, how were we actually training these text classifiers? I blame the course assistants who gave the lab sessions, but how did you train them? Or how did they train them?
The loss function and optimize it using gradient descent.
Yes, so some of the loss functions, but what were those loss functions?
negative log probability.
Exactly. So wait, negative log probability of what?
The positive and
What? So we wanted to minimize the sum of negative log probability of speak up. Correct answer given the input, right? So our machine learning model is going to give us the probability of anything that we feed in, right? We give here's the input. I want to know the probability of, let's say, positive class, negative class. It's going to give us that number. But what is the number that we want to increase? Is the probability of the correct class to which the input belongs. Now here, what was the goal of the language model? We want to ensure that our language model is going to put high probability on a text snippet that was drawn from the real true language distribution. So we want to maximize the low probability of correct text snippet. And that's precisely what we already have learned. In other words, although this is unsupervised learning, unlike supervised learning, nothing really changes. All we want to do is, we want to look, I'm going to assume that we now have a data. I'm going to look at all possible text that has been written down in a particular language or particular set of languages. I'm going to collect them from Wikipedia. I'm going to collect them from the internet. I'm going to collect the Amazon reviews. You might have to check with your lawyer whether it's possible, but let's say I'm going to collect them. Or I'm going to just use my journals that I have never kept, but assuming that you have kept it, you can use it if you want, right? As long as those are the valid text, you can use it. And then given this data set, or often we call it corpus because we're talking about the text here, we're going to look at each and every text X from this corpus. And then for each one of them, what do we want to do? We're going to compute what is the log probability of this correct valid sequence X. And we're going to look at the average of it. As we talked about earlier, writing down the total loss function as the sum is slightly confusing, and it's much better to look at the average. And then this is going to be our total loss function of this language model that's characterized by this set of parameters theta given the data set theta. This is almost exactly like what we saw, except the fact that earlier last week, our loss function was y given x. So that's the difference between unsupervised learning and supervised learning. But from the semantics, there is absolutely no difference. You might as well call that this x is just a concatenation of x and some, let's say, answer y. Who cares, right? But what we want is, we want to increase the log probability assigned to the correct or a valid instance from the data set. So that's what we're going to do. So same as before, we are going to do a maximum likelihood learning. Log likelihood. So it's really, I guess.
Can you just describe the data, like, I know data is usually like a parameter set, like what does it actually look like?
We'll look at that, yes. We're going to look at what kind of thetas we can have. Yeah.
I'm wondering how this works because you're not giving it any negative examples.
Oh, yeah, that's a.
Like load, like you try to do load balancing.
Uh-huh.
Like what's the problem?
Yeah, so this is a really interesting question. So how does this work when we only give the correct answers, right? That's the question. But in supervised learning, we also gave only the correct answers. How did it work?
You reduce the probability of generating the false answer.
Okay, but how did it happen? So by maximizing this, how did actually our model know to lower the probability of incorrect answers?
Is it by nature of like initializing randomly your weights?
No. Softmax, the normalization, right? So the probabilities assigned to all possible values of this y or x have to sum to 1. Now what that means is that when we try to increase the probability of the correct or a correct, let's say, sequence or a valid sequence x, it has the effect of decreasing the probability of all the other possibilities. And then we do that over all those valid sequences, thereby, in fact, eventually at the end of training or learning, those sequences that do not appear in D tend to have lower probabilities. So that happens automatically due to the fact that we are working in this probability space.
How do you manage like overfitting? How do you not overfit to your given data set?
Oh, how to avoid overfitting? Oh, that's a great question. But I thought the introduction to machine learning or the mathematical methods for data science should have taught you already how to avoid overfitting. That's slightly out of the context at the moment, but yeah, you will talk about some of them during the lab sessions. The same techniques that you have learned to avoid overfitting for any other problems apply here as they are. So it's really nice. I mean, all we need to do is just increase the probability of the correct one. And then because we said that we're going to use the autoregressive modeling or use the chain rule of probabilities, we can rewrite this now slightly further. Autoregressive. So L theta D is negative 1 over the size of the data set, xd log t x, and theta is identical to 1 over the size of the data set. We're going to go through each and every sequence separately. And then because we're in a log space, right? Log probability, not the probability space, instead of product, we get the summation over the length. Now t, small t goes from 1 to capital T. I'm going to put n there to indicate, oh, I'm sorry, it shouldn't actually be n. Actually, let's change it a bit. N from 1 to the size of t. And then this Tn refers to the length of the nth example. Because every text snippet you can imagine is going to have different lengths from another text snippet. So we need to think about that. And log probability of, so I'm going to still use the order, the permutation, but I'm going to drop it after this, of the t, let's say the variable x, given all the previous ones. 1, 2, O t minus 1. And then, so this is going to be our loss function. And then from here on, I'm going to assume that this O, this permutation is just an identity function. So this is going to be our loss function to train a autoregressive language model. And it's interesting, right? So looking at this, we get 2 different types of the loss functions. So earlier last week, we looked at two different types of, we get 3 different types. There was 2 different types of loss functions last week. One was the total loss function. That was the sum or average of all those per example loss functions. Now in this case, we actually have 3 different types of them. The first one is per step loss function. It's a per step loss function. And then we now have the sum of those per step loss function is now per example loss function. And then the average of all those things is the total loss function. So it's important to see it here, at least under what we have talked about, under this framework of doing relatively correct, not perfectly correct probabilistic modeling or the probabilistic language model, we average over examples, and then that allows us to use a stochastic gradient descent but we sum over the steps or the rows. It's a subtle point, but it's quite important. And then you have to, depending on your ultimate goal of how you're going to use a language model, that choice may have to change. But this is the most basic and principle driven according to this probabilistic language model. So you sum over the time step, then you average over the examples within your mini batch or across the entire data set. And then it just naturally arises from our desire that we want to increase the probability of each and every sequence in our training data. Now, let's look at this per step loss function a bit more. If you look at per step loss function a bit carefully, well, probably not even carefully, in first glance, what you notice is that it looks exactly like the loss function that we use for training a text classifier. Right? So let me just rewrite this per step log probability here. So it's the log probability of the, let's just use t instead of O because O is going to be identity, xt given x1 to xt minus 1. So this is the log probability of the correct word at time step t given all the previous words. And that's actually exactly what we used last week for text classification. Log probability of the correct class to which the text belongs. So it turned out, in the case of this particular choice of autoregressive paradigm for doing probabilistic language modeling, with the choice of the identity or a permutation function, what we observe is that it just becomes a text classification problem where the classes coincide with all the unique words in the vocabulary. And then we are trying to classify any given prefix of a text into one of these classes where each and every class corresponds to each and every unique word in the vocabulary. So we're solving the problem of classification. That's the reason why I actually did talk about the importance of the text classification last week, is that it is really literally a classification problem. So probabilistic language model, which we actually did look together as unsupervised learning, turned out to be solvable as supervised learning with a particular structure. So for instance, what would be an example, right? Let's say I'm reading the text, and then I was reading one text and one sentence, and then it started with New York. So New and York. Then the problem I'm solving is that should this New York, this two words sequence, x1, x2, belong to or to be followed by university, city, state, so whatever you can imagine, right? So it's a text classification problem. We're just solving as many text classification problems as there are words in any given text. What it tells us is that we just look at the log probability assigned to the correct next word, given the prefix, and then we sum all those scores, and suddenly we get a per example, there's a per sequence log probability. And that's what we wanted to do, wanted our language model to compute, right? Given us text, feed it into this black box, and then this black box should just give us a one number that corresponds to how likely, how probable this given sentence is. That's why we spent a whole, let's say, lecture last week on text classification. All right, so we are actually, okay, so let's take 5 and then come back at 6:05. Yeah, you can Yes, unfortunately, no. Whatever you can do, yeah, I had to figure out some ways that are the same. And that's oh, you're seeing it from there. Wait, where did I'm at the All right. Okay. I know 5 minutes are way too short. I know. Well, what can we do? So now let's think about how to solve this problem as any idea how to find this data. Right? So this data is the one that characterizes language model. Oh, by the way, before we continue, there was a request that for me to clarify what it means for this to corresponds to text classification. Now you can imagine that any given text belongs to any one of the classes that corresponds to one of the words in the vocabulary. This is any given text. And then this is the class to which this text belongs. Now it's just confusing because you think that, this one uses XT, and then the input and output have shared the same space, same set, vocabulary set. But what you can imagine is that, here's a vocabulary set, it follows a vocabulary set B. This follows the set C, and C equals B. So that's the kind of the importance of trying to abstract out yourself from the actual surface form. Of course, if you look at the surface form, it's like how we're predicting the input test field. But you can imagine that this one is just a class. You can replace it with a YT, and then you get the same supervised learning loss function. But you realize at the end, you just write the YT equals XT. Right? So that's a simple way to go about it. Yes.
So are each of those individual xi's, are they like word embeddings then?
Well, I think those are going to be the words. Now, how are we going to represent is up to us. And in this class, what we're going to do is we're going to do exactly what we learned last week. We're going to represent it initially as a one-up vector, but then we realize that by multiplying the one-up vector with the range matrix, we just get the vector-based word embedding that can be updated all together. But we'll get to that. We'll get to that. But yes, the choice of how you represent it is up to you. Okay, all right. So everything is so far so good. All right. Now let's see how we can estimate these low probabilities. So if I rewrite the P of XT given, I'm going to use this a smaller than T in order to indicate all those words that came before XT. And this is same as writing XT over P of X smaller than T. This definition of the conditional probability. And then this is same as writing P of X smaller than T and XT over sum of X prime. So we're going to go over all possible words in the vocabulary B, and then we're going to sum X smaller than T and XT equal X prime. So here the definition of conditional probability, here the definition of marginalization. So we marginalize out this variable, and then we end up with this. And then how do we marginalize it out? We try every possible value, and then sum the probabilities. And now let's see. and we continue. And then what we realize, the interesting thing is that we can rewrite it as P tilde smaller than T and XT over Z over sum X prime B P tilde XT equals X prime over Z. So what this Z is just a normalization constant. What this means is that instead of writing it as a probability, given any probability, you can always rewrite it as some scaled, right? Unnormalized probability. So that these probabilities, you sum them up, it's not going to sum to 1. But as long as you know what the Z is, you can always divide it by Z. So it's just a not even clever, it's a dumb trick to rewrite the whole thing in this way. And then what you get is, you realize that these Z's cancel each other. And what this actually tells us is that we don't need the actual probability of these subsequences, right? So X going from 1 to T, but all we need is some value that's going to be scaled version of the actual probability on both the numerator as well as the denominator. I know.
Sorry, like what did you circle again? Like why did you circle?
This one is cancels each other.
Oh, cancel. Okay, thanks.
I don't know, that doesn't look too mathematical, right? If you had a circle there, but okay, understandably makes sense. All right. So what this actually tells us is that there are many different ways to estimate this probability, and then one way we can go about is forget about the fact that it's probability, and then take an approach that is I'm going to refer to as the count-based approach or the estimation. So what is the count-based estimation? Let's imagine we're going to toss a coin, right? Coin. Okay. Yeah, I know all the crazy things happen when you teach, so it's okay. Let's say we have a coin, but when unsure whether this coin is unbiased in a sense that when I toss the probability that this coin that's heads or tail, I don't know whether it's going to be 50-50. Maybe it's not. So I want to know what is the probability of this coin landing here. So then I'm going to toss it n many times, and then it turned out that there were n many times it landed heads, and then you had the n minus m times tails, right? So n times I tossed it, and then I end up with the m heads and n minus m tails. Right? So then what is our best guess of probability that the coin is going to land on head after this n many tosses? What would be your answer? Okay, that's great. I mean, otherwise we'll have to actually go all the way to the probability one, and then you have to start everything. M over n, and then probability that is going to land tail is going to be n minus m over n. Now here, what you notice is that thinking about that, the actual number of occurrences of the coin landing head can be thought of as a unnormalized probabilities. So these two probabilities, right? There are two possibilities, two probabilities, you sum them, they sum to 1. But then here, this n, the capital N, is a normalization constant. And then we can only just look at the m and n minus m, the counts. In other words, if we have some data of the things that are happening, then to get this estimate of the probability, all we need is to look at the count. We just need to count the number of times this prefix, this text snippet appeared. And then I count number of times this particular text snippet appeared. I don't really need the actual probabilities of these texts, but all I need is that how often they appear. Because this normalization constant Z will be canceled out. So that's all we need. And you see why it's a count-based estimate. All we need to do is we just count. And that's it. Yes.
So in, when you canceled out the z's, does that assume that the partition function of the numerator and the denominator are the same?
Oh, it has to, because I'm using the same function. P tilde. Yes. So then let's try to do language modeling without stochastic gradient descent. Was there a question? No. Okay. So then our maximum likelihood estimation. Which actually turned out to be equivalent to count-based estimation when we can, is simply the probability of some event, right, happening is going to be the counting the occurrences of that events, and then just dividing by the count of all the other events, including itself, right? So this is the whole thing. And in language model, that is what we're going to do. So I'm going to use another color to indicate this different thing. So going from here, what we do is that we're going to count how often true text, right? True text appears, and then divide it by all possible hypothetical text, where the hypothesis corresponds to just replacing the last word in this text with all possible words in the vocabulary. So this is going to be our count-based estimate. So what do we need to do? We just count. We just have a large data set. We just go there, and then let's say I want to compute what is the probability of city following New York. I'm going to count every occurrence of New York City. And then I'm going to look at the counts of the New York, New York City, New York University, New York Fire, New York Police, New York Times, New York Cat, New York Dog. I will go through all possibilities, count them, and then sum them. And then I just divide the original count with that one. And that's how I'm going to get the probability of city following New York. That sounds easy enough, right? Yes, yes. And then what this means is that this count of all those texts, all possible text, is the theta in this case of the count-based language model. So there was a question about what the theta was. And theta is all those counts. You can imagine that this theta is a gigantic table where each row corresponds to any possible text prefix, and then there will be a number that is a count associated with it. That's the theta in this case of the count-based language model. Now this one turned out to have a bit of an issue, and that issue is issue of the sparsity. So why is this sparsity an issue? Let's think about it. What is the number of all possible phrases of length t, given a vocabulary size of vocabulary v? The number of all possible phrases of length t is going to be the size of vocabulary to the power of t. And then we are looking at all possible things. And in particular, if you look at the near the end of any kind of given text, the t is pretty long, right? That's capital T. If I'm doing the language modeling over paragraphs or the sentence, let's say sentence is much shorter. Sentence, in English sentence, if you count the number of the words, the average number of the words, in the newspaper or the formal text, is going to be about between 23 to 26 words long. Now, the vocabulary size in the word in English is going to approach the million. Million to the power of 26 is actually really, really large number. It's almost as large as the number of atoms in this universe. In other words, whatever this value is for any moderate size t, this size is going to be so much larger than the size of the corpus or the data set itself. That's the issue. What that means is that it's almost any phrase that you think of, you won't see the phrase in the text. Well, why is it a problem? If you don't see them, you just say that the count is 0, then maybe that's fine. But the issue is that the count 0 or the 0 count does not imply that a given sequence is impossible. You can imagine that if you try to go to, let's say, Google Ngram Viewer, which is available for all of you to look at, and then if you type any perfectly, let's say, formed sentence that's going to be some introduction of some person, and then you put my name there, the count goes to 0 overnight. But that doesn't make the sentence invalid, right? It's still a perfectly valid sentence. Or if you imagine that you read some of these the latest papers, right, academic papers, they are supposed to come up with some new concepts and explain them in a way that is different from earlier papers. Those are all going to have the count 0 according to your corpus because that kind of thing was never written before. So what that means is that the 0 count does not imply the impossibility of a phrase, but due to this exponential growth of the space or the set of all possible phrases and our fixed corpus, often corpus doesn't grow exponentially almost never, except for at the beginning of the internet boom. But none of you are using internet back then, so you didn't know. But then we actually did have an exponential growth of the size of the corpus. What that means is that we're going to get a lot of these plausible phrases that never appear in our corpus. Very important to remember. And then this is the issue of the sparsity. It's fine to have 0 counts, but it's not fine that we don't know whether a 0 count phrase is impossible or we just did not see them because our corpus is limited. In order to avoid this issue of the sparsity a bit, not too much, so people have been relying on something called nth order Markov assumption. In nth Markov assumption, we say that the probability of xt given x1 all the way to xt minus 1. So the conditional probability of the xt given all the previous words or the previous words is going to be same as the probability of xt given all so the n previous words. Could be n minus 1, doesn't really matter, or phi 1 is fine here. So what we're saying is that to get the probability of the word at the position t, we should have looked at all the previous words. But with the nth order Markov assumption, we're saying that we're going to only look at the n previous words and ignore any dependency on a words that were further away than the n steps. And then what this allows us to do is to control the degree of sparsity with this n. So this n is the key here, right? So if you think about the degree of sparsity as the ratio between the size of your corpus and the size of your all possible, let's say, phrases. Then by using the nth order Markov assumption, the ratio is like this, which is substantially smaller, greater, I'm sorry about this, which is substantially greater than the ratio between the size of the corpus and the all possible sentences. So it's like the d over, let's say, size of the vocabulary to the power of, let's say, 2 or 3 versus originally, without this assumption, we would have to look at the sparsity of the d over size of the vocabulary to the power of, let's say, 23, 26. The difference is humongous. By choosing a small n, we can actually control this sparsity. Right.
What ends do we normally see in practice?
In practice, and that actually is dependent very much on the language that you model. In the case of English, it's quite often to go up to about 7 grams, but you need to use other techniques that you're going to learn in the lab session to avoid the sparsity that comes from the fact that we're using 7. It's just all notation from the computation complexity. Is there any another question there? Yes.
Is there a reason we only go forward?
No, we don't have to. I just because as I said earlier, permutation can be arbitrary, and then you just to avoid writing all over and over. I just said okay, full identity. Yes.
Wait, Professor Cho, is that equal P xt given x c minus n, or is that t minus n?
Yeah, t minus n.
Okay, thanks.
So this actually does help quite a bit. Now, what that means is that under this nth order Markov assumption, the probability, the conditional probability xt given xo the smaller t is same as the probability xt given xt minus n to xt minus 1. And this is going to be estimated by our count-based estimation technique. That is that we look at the count of this n gram or the n plus 1 gram, doesn't really matter. Just and then we're going to look at all possible hypotheses, hypothetical, let's say, n grams. So this now seems a bit manageable. So we only look at the n grams, right? So the fixed n, and then we only get the n grams. And what we do is we just go through the corpus, every single text we have, and then extract all those possible n grams, make a gigantic table, gigantic hash table, where the key is going to be n gram, and the value that's going to be stored in the hash table is going to be the count. Obviously, do not use hash table. Do not use hash. You're going to use other better structures for storing this n gram or the n gram count, which you will learn this week at the lab session, tomorrow and the day after. Even then, it's still an issue. The sparsity is still an issue because our corpus size is still small. And then as we have learned from this pandemic, the exponential function grows so fast. And then somehow the entire population of the earth realized it only last year when all the computer scientists and mathematicians knew about it. But so the sparsity still exists. Still, when we encounter an n gram that has 0 count, we can't tell whether that's impossible or it's just an artifact from having a small or weird corpus we have. So how will we actually avoid this issue? And then, well, if you believe that no, that's not true. Google or the entire internet has all those essay texts, so everything is possible. You can go to the Google books, the n-gram viewer, pick any period, you try to type in whatever you want, you'll find that a lot of n-grams do not appear, although they are very, very possible. Something like if you look for, let's say, a tiger is chasing a llama, you're going to see that that has a 0 count. Soon it's going to be updated because I've been using the example myself and then ongoing. So then how will we actually avoid this issue? We're going to talk about just one quick way to avoid that issue. And then one quick way is something called smoothing. The smoothing is same as turning this maximum log likelihood learning into maximum a posteriori learning. And then if you recall the difference between these two, the first one, we don't care about the prior knowledge. We only stick to the actual data that we see. On the other hand, maximum a posteriori learning, we do now care about the prior to a certain degree, So you can think of this smoothing as the math version of what we did above. And then what is our prior here in this smoothing is that the every possible n-gram has a chance of appearing at least epsilon number of times in this universe. So how do we implement it? P of xt given x smaller than t is same as P of xt given xt minus n to xt minus 1. So this is the Markov assumption. And then we write this, and let's just do some copy. If we could put here. Now here what we do is we add some epsilon. So this is our prior. Our prior says that let's imagine that this n-gram that we are seeing here has a count of 0. So C of that n-gram is 0. But we are saying that well, that cannot be the case. Because our prior knowledge, and the prior, what is the prior knowledge? The knowledge before you saw the data. According to your prior knowledge, before seeing the data, you know that every single n-gram you can imagine must appear at least absolute many times. And then that applies to all the counts in the denominator as well, which is same as adding the epsilon times the size of the vocabulary. So this is a one way to avoid the issue of the sparsity. So essentially, but this one is not that great because it still doesn't distinguish between the impossible n-gram and plausible n-gram. Although it does avoid some issue of the IP0 probability. So the better technique, another technique that is better is something called backup. So if we can't really trust, we see that the count of some n-gram is 0. We're going to try to back up to a n-1 gram and then see if that count is 0. If that's 0, we're going to back up again. And then you can imagine that we can go back up all the way to the unigram that is just a word. But we know that our vocabulary is fixed, and then we're going to assume that our vocabulary is exhaustive. Then we at least get some count. Now it's a bit tricky. We can't do the maximum likelihood estimation because we're not looking at the same kind of variables. But for that, I think that Jason Fang and all the other course instructors are going to teach you probably not how to avoid that issue, but why that helps, and then what is the right tool to use. There was a question?
So for an n-gram, we can just check whether that is like grammatically correct. If so, then we can add it. Otherwise, we can make it impossible.
That's an interesting question. So can we actually check whether this n-gram is grammatically correct? And then if so, then we're going to add epsilon. If not, we're not going to add epsilon, right? You'll be quite surprised, but checking the grammaticality of any given text is an unsolved problem, and it's probably ill-posed problem. I know you all probably have tried the Grammarly, and the Grammarly is saying that you're wrong and they are right.
We could
In
check,
many cases, they are wrong.
we could check how close we are to the grammatically correct.
No. Only if I knew, then I would make a startup that's going to compete against Grammarly and then win. Yes. Yes. So that's actually a really important problem that a lot of people want to solve, especially in the education sector, but it's not. It hasn't been solved. Yes.
What exactly do you mean by impossible sentence or something like that, or impossible sequence? If we don't even, if grammar's not well defined and things are like that.
That's precisely the point. Yes. What I can't even tell which phrases are impossible. So then, among the zero count phrases, how do I know which ones are impossible? That's exactly the point that we don't know. If we knew, for instance, by checking the grammaticality, then we wouldn't have this issue. That's precisely the point.
So what's the point of disambiguating these two things?
Well, maybe so we could actually say that we give up, or we try to we can solve it in another way.
When you use the method you mentioned last, where you back up to lower grounds,
Yes.
How do you normalize the counts?
Yeah. So that's a good question. So if we do this, use this technique of backup, what is the right way to make it into the actual probability? That does involve quite a bit of mechanism. You can actually make it explicitly normalized. You can actually do that by looking at how the size of the all possible n-grams shrinks or increases, and then you can account for that by counting all of them. But that turned out to be too expensive in general. So what people do in practice is to learn to normalize it approximately. But that's a bit out of the content of this course. You can look it up. It's called backup. There are many different ways to do so. The most popular one is one that used by the proposed in 1996 by the Kneser and Ney. All right, so we have just learned about the count-based language model, and then you should be able to implement it. So, but then let's try to think of quickly where this sparsity actually comes from, and then try to connect that to what we learned last week. So this issue of the sparsity, where does it actually come from? It turned out that the one way to think about where the sparsity comes from is the nature of exact matching. So only way for us, and then let's connect it to one-hot encoding. So what we have so far done, and then we're going to stick to this idea, is that if we don't know the similarities among the words ourselves, a priori, we don't know. So how do we actually encode those words? By encoding them into the code, or the code that is most agnostic. And then what was it? You take any pair of distinct words, and then you compute the distance in this encoding space. That distance has to be constant regardless of which pair you pick. Only time that distance is going to be zero, different, is when you pick the same word twice. Right? So that was a one. And then what that means is that we are looking into the exact match. So given any two words, the distance is going to be zero or some constant. I'm going to just use one, but you can always scale it with some scalar, positive scalar, if W equals B, and then otherwise it's just one. This is equivalent to saying that how we are going to encode W and B, which is from this vocabulary, using one-hot encoding. And then why does this actually imply the sparsity is that if, as soon as we get an n-gram, a pair of n-grams, as soon as there is any one word difference between these two, the similarity between these two is zero. Yeah, zero. Wait, one or distance. Dissimilarity is zero, right? So for instance, a lion is chasing a deer. So that's going to be the text we're going to think of. And then a lion is chasing a llama. In our mind, these are pretty similar sentences, right? They're effectively the same thing if you haven't seen a llama or if you haven't seen a deer, or in the context of thinking about a predator chasing a prey, essentially the same. But according to our criterion, they are different. They are very, very different. They are as different as saying a lion is chasing a Mars. It's as different as that. And then maybe the reason why the sparsity issue arises. Now let's imagine that trying to estimate the probability of deer following a lion is chasing, and then trying to estimate the probability of llama following a lion is chasing. The latter one is going to have probability of zero, because a lion is chasing a llama never appears. And going to the Google Ngram here, it's actually zero, counts zero. On the other hand, a deer following a lion is chasing does appear. So the probability of that is going to actually reasonably high, because there aren't too many things that lion is chasing, right? But from our our perspective, they should actually have a similar probability. Because the llama is very likely to show up, and then only if I knew, or our system knew, that llama is a mammal that is often a prey rather than a predator, and lives in let's say the mountains, but let's say mountains, just like a deer is, right? Deer is more of a prey than a predator, lives in a forest. Only if our system knew the similarity between these two, then perhaps our system could have said that the probability of llama following a lion is chasing should be similar to the probability of deer following a line is tracing it. So in other words, the issue of sparsity seems to arise from the lack of the notion of similarity between words. Then what can we do? We just want to give our system or the model, our language model, the ability to capture the similarities. And this actually does connect to exactly what we learned last week, that is the text classification. And if you recall from the earlier today, in this autoregressive way, if we look at this per step loss function, this per step loss function is exactly the loss function used for text classification. So instead of doing this counting, which was pretty nice because we knew what is the exact answer we can get, we're going to now advance to a so-called feedboard language model. This feedboard language model is going to be just like a text classifier. And how do we make the text classifier? We need to define some parameterization of it. That's going to take as input xt minus n, xt minus n plus 1, all the way to xt minus 1. And then x is going to take the input and possible follow-up, let's say, the possible word that follows the input. And then what it does is that it's going to just compute the score. Right? And then we know how the score is often computed. In this particular case, we're going to have the class embedding that corresponds to the word that follows, transpose some representation of the input, which is going to be t minus n, all the way to xt minus 1, plus bias associated with this class that is the next word. And with this one, we use softmax, and then we suddenly get the text classifier that tries to compute the conditional probability of the next word given all the previous words. Then by asking this machine, what is the probability assigned to the correct next word, and then just train them by multiplying everything for every location, we now have a language model. Now by doing so, you know that as long as we can come up with a way to encode this x using a continuous vector representation, and then trying to maximize the log likelihood or trying to minimize the average negative log probability of the correct next word given all the previous words or the n many previous words, we know that the representations of these words are going to evolve or will be estimated in a way that the similar words are going to map to a similar point in this representation. Just like how we did with the sentiment analysis. All the words that are associated more with the positive are going to have a similar vector representation, and then thereby from the perspective of the class embedding or the scoring function, they are all the same. Now, in this case, any words that appear together or they appear with the next word, these words that we want to look at, they are going to have a similar embedding to the class embedding of this following word, and vice versa. The class embedding of this following word is going to be similar to all the embeddings of the words that preceded this. And this actually does let us come back to the idea of the distributional hypothesis from the beginning. By building this probabilistic language model and using the idea of the autoregressive paradigm, we saw that computing the log probability of any given sentence is identical to computing the log probability of the next word given all the previous words. Now we're using the n-grams Markov assumption at preceding n words and then sum them. And training this feedboard language model or the text classifier allows us to estimate the embeddings of the words such that the embeddings of the words are going to be similar to the word that immediately follows the second one. So when these words appear together with that word, the embeddings are going to be all similar. So any embeddings we get from this n-gram, any n-gram that we take, this phrase, will be similar to each other because they all have to be well aligned with the classic value of the following. Now, once that happens, this issue of sparsity disappears because the comparison that we make is not in this way, but this comparison is the dot product. And dot product of the continuous vectors where it's very rare that we're going to get 0. And also, depending on which context that particular word appeared, even in a new context, if the new context makes sense for other words that have similar embeddings to this new word, our language model will be able to give us a non-zero probability or the non-zero count. And you can imagine why that's going to be the case, because let's imagine the llama example again. Let's say my corpus consists of, let's say, Wikipedia. Wikipedia definitely has an entry on llama. In that page of llama, it doesn't really talk about lions, because lions and llamas actually do not live in the same continent. So llamas live in the South America, lions does not live in the South American. Now, deers, on the other hand, deers do live in the same continent as the lions. And then in the Wikipedia page of the deer and llama, you're going to see that a lot of words appear together, right? On both sides, a lot of words appear. What that means is that our language model is going to make the representation of llama and representation of deer very similar, very close to each other. It just has to happen because they often appear in a similar context, in this n-gram context. And then later in the test time, if I wanted to compute the score of, and then that's going to be the same for the class embedding as well. Now, what is the probability of llama following a lion is chasing up? That's going to be very, very similar to the probability of deer following a llama, the lion is following up, because a lion is following up is just fixed. This is shared between these two. All we need to ensure is that these class embeddings of the deer and llama are similar with each other. Then they have to, because they did appear together in this context with other words only. So their embeddings are going to be very similar to each other. Thereby, the scores assigned to llama and deer following a lion is chasing up will be similar. Thereby, the probabilities are also going to be similar, although that phrase, a lion is following a llama, has never appeared in our original training corpus. Now, that's how we're going to solve a bit of an issue with the sparsity. Not fully, we're going to learn about how to solve the remaining issue with the sparsity next week. All right, class dismissed.